So now we're going to finish up our 9.4 notes by talking about how to add up all of the terms in a geometric sequence. This is the formula for adding up the terms in a geometric series. So the most important values, the things you'll need to identify, are the first term in the sequence, what the R value is, so what it's multiplying to go from one term to the next, and you'll use that in both of these locations. And then the N value is how many numbers in the sequence altogether that you're adding up. So here's our first example. Now, by looking at the list of numbers they've given us, we have a sub 1. We don't need to do any solving for that. The R value, the easiest way to find R is to pick any number in the pattern and then divide by the number in front. It doesn't matter which number you pick. As long as you have one in front of it, you can pick a term and divide by the one in front. And in this case, I'm getting that R is equal to 2. The last thing we need is how many numbers there are altogether. Now, unfortunately, they didn't list all of them out, so I can't just quickly count them up. This sequence probably isn't that big, so it wouldn't be too hard to just sit there and keep multiplying by 2, multiplying by 2, multiplying by 2, and fill in the missing terms. But we also want to make sure that we can do this with the formula as well. So since this is a geometric sequence, I'm going to set up the formula a sub n, which in this case, I actually know that a sub n equals 768. I have a target term in mind, so I want to know how many numbers into the sequence this one is. So a sub n is going to equal 768. The first term in the pattern is 3, and R is 2. So my next step here would be to divide both sides by 3. And then one trick you can use on this is figuring out 2 to what power equals 256, which in this case is 2 to the 8th power. You may remember a way to find that value using logarithms, or you could always just kind of guess and check and say 2 to the 2nd power and just keep multiplying by 2 over and over and over again until you hit the target number. And the reason I'm doing that is because when the bases of the two exponential terms match, so I have 2 to the 8th and 2 to the n minus 1, then you can just set the exponents equal to each other. So now I have a much easier equation to solve. 8 equals n minus 1, which means n is 9. So now that I have the 3 values we need for the sum, a sub 1, r, and n, let's look back at the formula so we can plug the numbers in. So I'm going to have the sum of the series is the first term times 1 minus r to the n over just 1 minus r. So s sub n equals 3 times 1 minus 2 to the n over 1 minus 2. If you simplify this a bit, you'll have 3 times negative 511 all divided by negative 1. So the negatives are just going to cancel out, but I do need to evaluate 3 times 511, which is going to be equal to 1,533. So that's our final answer. That's the sum of all of the terms. Even though we didn't have them all listed out, there were some numbers we didn't even figure out. Now I know that adding them all up equals 1,533. Here's a second example. It's going to be very similar, but they've given us slightly different information. This time we don't know what the last term in the sequence is. We just know how many numbers there are. So again, if we find R, we could sit there and then just keep multiplying the number out, but you're going to get some pretty big numbers in there. And I want to try to emphasize how to do this with the formulas instead of by plugging and checking with the calculator as much. So let's start by identifying which information we already have. We know that the first term in the sequence is equal to negative 1. And we know that n, altogether we're going to be adding 9 numbers. And then finally we need to figure out what r equals, which we can determine by picking any number in the sequence and dividing by the one in front. So try to pick the easiest numbers to work with. In this case, if I say 8 and divide by negative 1, then I get an r value of negative 8. So this actually has all of the information we need to use the sum formula. So by looking at this, all I needed was a sub 1, r, and n. So we're ready to actually plug in and evaluate the sum of a sequence right now. So s sub n is going to equal a sub 1 times 1 minus r to the n all over 1 minus r. Now the use of parentheses is very important in this case because my r value was actually a negative, so that does affect things like the exponents or when you're subtracting a number. So I wanted to be careful and make sure that I'm including the fact that r is a negative 8, and that's what I'm raising to the 9th power from our formula 1 minus r to the n. The entire number with the sign included needs to be raised to that power. So now to simplify this a little bit, you're going to get a pretty big number with this because negative 8 to the 9th power is huge, and then you're doing 1 minus that value. So I'm ending up with 1,3,4,2,1,7,7,2,9. And all of this is going to be divided by 1 minus negative 8. The double negatives cancel out, so you're dividing by a 9. However, I do still have that negative 1 out front that's getting multiplied in. So that's going to change the sign on the term and take it back to negative 149,13,081. And that's why it's good to try to rely on using the formulas more, because you don't want to have to list out some of those ridiculously large numbers. And then especially when the signs are going back and forth, it's very easy to accidentally input something incorrectly into the calculator and get the wrong answer from that. So this isn't a slide you need to recopy, not this stuff at the top anyway, because we've already talked about how a sequence lists the terms in a pattern, and then the series adds them up. What we did not talk about, what I added to this slide, was this other notation for writing a series. So there are 3 important pieces to it. There's the piece underneath, the piece off to the right, and the piece on top of this symbol that we call sigma. So this sigma symbol, the number underneath is indicating where your sequence is starting from. What is the first term that you're plugging into it? And usually it's going to begin with a k equals 1 or an n equals 1, whatever variable you have, because it's saying that you start off by plugging 1 into the sequence, and then that's the first term in your pattern. The information off to the right is your explicit rule, and then the number on top is what is the last number in your sequence that you're going to be adding up. So if you're adding up 10 numbers, then this number on top will be a 10. If you're only adding up 6 of the numbers in the sequence, then the number on top will be a 6. So here's where I have that information written out. So that's called summation notation. And if you are trying to write a sequence in summation notation, the first thing you do is you write the explicit rule, and that goes on the right-hand side of the sigma. That means it's the formula that has an a sub 1 in it, and then either a d or an r, depending on whether it's an arithmetic or a geometric. Next, you have the n value for the first term going underneath the sigma symbol. Like I said, that usually starts from 1. Usually you start off by adding the first term in the pattern. There are some situations where maybe you're trying to add up how many seats there are in a theater, and maybe for this particular performance, you're not going to be able to use the first 2 rows because the cast is going to be using them to jump up on stage at various points. So maybe you're figuring out the seating capacity, but you need to ignore the first 2 rows. Then you would be starting from n equals 3 in that case, starting from the 3rd row in the theater and going backwards. And then the last number, if you have 20 terms in your sequence, that number goes on top. So sometimes you'll be asked to evaluate a series, and it'll be in this form instead. Now you'll want to be careful and make sure you correctly identify it as a geometric or an arithmetic first, because they do have slightly different formulas for the two. So in this example, if I was trying to list out some of the terms, I'm starting from k equals 1. So imagine what happens if you plug in k equals 1 into that explicit rule. Then I would have 4 times 1 minus 1, so the first term is 3. Then I would go on to the next term in the sequence. I'd be plugging in k equals 2. Well, 4 times 2 minus 1 is going to equal 7. And then the next term would be 3. 4 times 3 is 12. Minus 1 is 11. So at this point, you can probably see which type of sequence we have. As I plug in more and more numbers, it seems to keep adding 4. So this must be an arithmetic sequence. So the rule for S sub n for an arithmetic sequence is n times the first term, which we already found is 3, and then we need to add the last term. Now I don't have the last term yet, but we can go ahead and fill that in real quick because the last number in the sequence is going to be the 15th number. So if I plug k equals 15 in, that will be the last number in my pattern. So 4 times 15 is 60, minus 1 is 59. So I know there are a bunch of numbers in between, but I don't actually care about all of them. I just care about the first one and the last one for this sum of them all. And then it's the average of those two things, the first and the last. So add them up and divide it by 2. So now just to simplify what I've written here for the sum of an arithmetic sequence, I have 3 plus 59, which is equal to 62. And I demonstrated this before. It doesn't actually matter if you do 15 divided by 2 or 62 divided by 2. Pick the one that's in even numbers so that it's a little easier to compute. In this case, half of 62 is equal to 31. So now you can just say, what is 15 times 31? And your answer is going to be 465. So again, that's instead of us listing out all the terms and then sitting there and adding them one at a time all the way through. So there will be a problem on your test where you'll have to deal with getting a geometric or arithmetic series given in this form. So make sure you are comfortable with how to find the terms in the sequence by starting from the bottom number and then ending with the top number. And then this is your explicit rule. So just like with other problems we did earlier, you can always find a specific term in the sequence by just plugging in the k value that you're interested in. If you want to find the 10th term, plug in 10. So that's all for the notes today. Thank you.